Today I'd like to talk about acid strength and the position of acid-base equilibria. And what I hope we're going to do is get a feeling for the strengths of different acids, both acids that we think of from general chemistry, typical acids, and acids that will come up in organic chemistry. I'd also like us to be able to get a feeling for the positions of equilibria involved in these acids, because this is really central to understanding organic chemistry, what's deprotonating what, and a lot of chemical reactivity. This is not so much going to be about calculations. We're not going to worry that much about equations, although I will give you one just to help you intuit what these numbers of pKa's mean. And that's where we're going to start, with some pKa's and some categorization of various acids. Strong acids are compounds that you would typically think of as acids. They're compounds that when you pour them into water, they fully dissociate to a proton and a counterion. They are the acids that you think of as acids that burn you. Hydrogen iodide and the hydrogen halides is one such acid. HBr, hydrogen bromide, hydrogen chloride, these are all strong acids. When you dissolve them, they generate hydroiodic, hydrochloric, hydrobromic acid. And sulfuric acid, of course, would be another. All of these acids fully dissociate in water. They all have a very significant pKa, a negative pKa value, pKa of less than -2. And by characterization, or by comparison rather, let me put up H3O+. And this is an important compound. You can't buy a bottle of H3O+. You always need a counterion. But H3O+ is what you get when you dissolve a strong acid in water. You also get the counterion. If you dissolve HCl in water, it essentially fully dissociates to hydronium ion, H3O+, and chloride anion. The pKa of H3O+ is -1.7. This is what's often referred to as the leveling effect. When you dissolve a very strong acid in a solvent where the protonated version has a smaller pKa, or rather a larger pKa, it fully dissociates. Question? The concentration of hydronium in a strong acid is very simple. If I dissolve 1 mole of HCl in a liter of water, it's 1 molar. If I dissolve half a molar, it's half a mole, it's half molar. So basically, all the HCl, or all the sulfuric acid, dissociates. So the concentration of hydronium ion is whatever I dissolve my strong acid. Okay. In weaker acids, you start to have equilibria set up. In these cases, in very strong acids, you're fully dissociated. Weak acids, the ones that you're thinking of. These are compounds that you would think of as acids, but not very strong. They're largely undissociated. Carboxylic acids, RCOOH, have pKa's typically around 4 to 5, and you'll see me writing a tilde a lot to mean approximately. We'll see examples where the pK of carboxylic acids are perturbed, but in general, carboxylic acid, like acetic acid, would be somewhere between 4 and 5. In general chemistry, students are often surprised to learn that hydrofluoric acid is not a strong acid, it's a weak acid. its pKa is 3.2. It doesn't dissociate a lot. It's not much stronger acid than the acetic acid in your vinegar. It will burn you terribly for other reasons, physiological reasons, and hydrochloric acid is one of the worst acids to work with. Moving down in pKa, the ammonium ion, NH4+, which we used in our previous lecture for an example of Equilibria, has a pKa of 9.26. And then, still weaker, water is amphoteric. If I have time, I want to come back to this at the end of today's lecture because this often confuses students. Water can act as either a base picking up a proton to give hydronium ion, or an acid giving up a proton to form hydroxide ion. As an acid, water is a weak acid. Its pKa is 15.7. There are a couple of compounds that we can think of that are sort of related to water in various ways. One is alcohols, and I've started to make the analogy between alcohols and water. A typical alcohol, you could say the pK is about the same as water. Methanol is pretty similar to water. Some are just a hair weaker as acids. 17 is a number. If you want to keep one number in your head, 17 is a good number, but nobody's going to fault you for keeping 16 for water and 16 for an alcohol in your head. Moving along the family, we'll talk about periodic trends in a moment. Thiols are pretty important in various organic reactions. Remember, sulfur is right under oxygen in the periodic table. Thiols are a little bit more acidic than alcohols by about 6 pKa units. Thiols have a pKa of about 11. That means if you dissolve a thiol in a solution of sodium hydroxide, you'll pull off the proton. We're going to come back to these equilibria in a moment, so I'll give some more sense to that. Last one I'll give is an example. Hydrogen cyanide. pKa of hydrogen cyanide is about 9. Hydrogen cyanide is sometimes referred to as hydrocyanic acid. It's an incredibly toxic compound. 50 milligrams will kill you. All right, the last category, and this really gets into compounds that are of a lot of importance in organic chemistry, are things that you wouldn't often think of as acids. I'm going to call them very weak acids. And I'll put acids in quotes. At the end of the last lecture, we got into a discussion of methane and how methane, no molecules of methane would be ionized in water. And yet I said the pKa's of organic compounds like methane and others are important when one looks at them in relationship or in reaction with other compounds. So just like water is amphoteric, ammonia is amphoteric. NH3 can act either as a base or an acid. If it acts as a base, we pick up a proton to form an ammonium ion. But as an acid, it gives up a proton to form an amide anion, NH2-. And one of the reasons I take ammonia as being important is it's the archetype for various amines, just as water is an archetype for alcohols. So I'm going to put next to ammonia RNH2. That's what we call a primary amine. If you want to be complete, you could also put R2NH. That's what's called a secondary amine. The pKa of ammonia and of primary and secondary amines is about 38. And I want to write very explicitly the conjugate base, just so we don't get confused. Just like with water, I said the conjugate base is hydroxide anion. With an alcohol, the conjugate base is an alkoxide anion, RO minus. And with ammonia, the conjugate base is NH2 minus. And with an amine, the conjugate base is RNH minus. So when we think about ammonia being a very weak acid, we think about it giving up one of its protons to form the amide anion. Hydrogen, not something you would think of as an acid, but it has a pKa of about 35. And again, I'm going to write the conjugate base, hydride anion. In the course of the A, B, and C sequence, you will see bases where amide anion or R2N minus or R2NLi is used as a base. You'll also see cases where sodium hydride or potassium hydride is used as a base. We talked a little bit about the pKa of methane before, and I'll just say in general, alkanes such as methane, so I'll write EgCH4. Have a pKa of approximately 50. The conjugate base, I think I'll stop, I'll just put a zero mark here, for methane would be CH3 minus. If we look at alkenes, for example, ethylene, now the pKa is a little bit less. Ethylene's a little bit stronger very weak acid than is methane. It's about 44. And again, we're talking a conjugate base now, and I'll write this out just so you can see it. Of a deprotonated alkene. Alkynes, for example, acetylene, are still more acidic. pKa is about 25. And the conjugate base is the acetylide anion. Pardon? Actually, great question. Will you be given the pKa values? No, actually. These are numbers you may not even want. At this point, I would say having these numbers at your fingertips, this very baseline is important, because what's going to happen is as you get more familiar, you're not going to be calculating. You're going to be intuitive. You're going to say, oh wait, yeah. Amide anion is a stronger base than acetylide anion, or acetylene is a stronger acid than ammonia when I mix sodium acetylide, when I mix sodium amide with acetylene, it's going to pull off a proton. And that's not a lookup. That's a thing. So having a baseline of knowledge is actually going to give you the power to think. All right, now I want to take these numbers for the rest of the lecture and play with them in terms of some ideas of position of acid-base equilibria and also some trends that contribute to acid strength. Position of acid-base equilibria. Very simple. A stronger acid and a stronger base react to give a weaker acid. weaker base. So if we want to think about this reaction as an equilibrium, I would draw my back arrow smaller. What do I mean in application? I mean, let's take NH4 plus, this is an equation you'd see in general chemistry, and hydroxide anion, and look at the reaction where ammonium gives up a proton to hydroxide anion, and we have an acid-base equilibrium to generate ammonia plus H2O plus water. First thing you do in thinking about this reaction is say, oh, this is an acid-base reaction. We're transferring a proton. Ammonium is acting like an acid. It's giving up a proton. It is meeting the Bronsted definition of an acid. Hydroxide is accepting a proton. It's acting like a base. Ammonia is the conjugate base of hydroxide, of ammonia, and water is the conjugate acid of hydroxide anion. Then you look and you say, okay, how do I figure out where the position of this equilibrium lies? All you need to do is look at the pKa's of the two acids involved. The pK of ammonia is 9.26. The pKa of water is 15.7. In other words, ammonium is a stronger acid than is water. You don't even have to worry about base strength. Conversely, a priori, that means hydroxide is a stronger base than is ammonia. So ammonium is a stronger acid than water. This equilibrium lies to the right. Let's now try the same concept with a distinctly organic flavor. We'll take acetylene and amide anion. You can't buy a bottle of amide anion. You can't buy any anion alone or get any anion alone, because if you put just anions together in a bottle, if I put a mole of anions together, they would repel each other in an explosion with such force it would destroy this lecture hall. But you can buy anions and cations together, so I would buy sodium amide, NaNH2. If I mixed acetylene with sodium amide, we would also have an acid-base equilibria. We would generate acetylide anion, and of course if we use sodium amide, sodium as the cation would come along for the ride, and we would generate ammonia. This reaction too is an acid-base equilibrium. Acetylene donates a proton to amide anion, so acetylene acts as an acid, amide acts as a base. We generate the conjugate base of acetylene, acetylide anion, and the conjugate acid of amide anion ammonia. Once again, to figure out whether this equilibrium lies to the right or to the left, we simply compare the strengths of our two acids. Acetylene has a pKa of about 25. Ammonia has a pKa of about 38. Acetylene is thus the stronger acid. This equilibrium lies to the right. And when you have differences in pKa that are substantial, these equilibria lie very far to the right. The position of this equilibrium lies to the right by 10 to the 13th in equilibrium constant. Let's try one more example. Let's now take methane, CH4, and our acetylide anion, and look at a reaction where the acetylide takes the proton away from methane. Once again, an acid-base equilibrium. Methane is acting as an acid. It's giving up a proton. Acetylide is acting as a base. It's accepting a proton. We generate acetylene, which is the conjugate acid of acetylide, and methyl anion, which is the conjugate base of methane. Which way does this equilibrium lie? To the left. Why does it lie to the left? You're absolutely right. pKa is higher, so the equilibrium lies to the left. pKa of methane is 50. The pKa of acetylide is 25. This equilibrium lies way, 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 way to the left. If I took my sodium acetylide and I bubbled methane in, just as we had in water, essentially no deprotonation of methane, no dissociation, we would have essentially no deprotonation of our methane by acetylide. I'll tell you a little bit more about how I can make those statements in a moment. But before we do this, I want to take those numbers we took before, the pKa's of HCl, the pKa's of HF, the pKa's of alcohols, the pKa's of thiol. And I want to make some sense of them, because these aren't just numbers, they're periodic trends. And when you can see the periodic trends and intuit the factors affecting acid-base stability, then you can get a lot of the information that's in that table, at least qualitatively, and you can start to know where many acid-base equilibria lie. The guiding factor in essentially all of acidity is stabilization of the conjugate base, stabilization of the species that results. And when you're generating an anion, all we really need to do is think about stabilizing the negative charge. As we go down the periodic table, pKa increases. We saw that hydrofluoric acid was only a weak acid, pKa of 3.2. Hydrochloric acid is a stronger acid. Its pKa happens to be about -7. Hydrobromic acid, or HBr, has a pKa of about -9. And hydroiodic acid is very, very strong with a pKa of about -10. It's the main factor here. You look at this, and as I said before, this is a little counterintuitive, because the first thing people think is, oh, electronegativity. Fluorine wants those electrons more. But it's not so simple. Although fluorine wants the electrons more, salvation and the energies of salvation are huge, and the energies of stabilization of an anion are huge. So there are many factors. The easiest way to think about this is, how do you stabilize the negative charge of the conjugate base? Fluoride anion is very small. All that negative charge is pushed together. Chloride's a little bigger. Bromide's bigger, iodide is still bigger. That negative charge is spread out the most. And that's a good general principle for thinking about acid strength. If you can spread out the negative charge, you have a more strong acid. We see that same principle in the oxygen column. We said that alcohols have a pKa of about 17. They are weaker acids than thiols, RSH. pKa of thiols is about -11. And although we're not going to talk about selenols, the selenium analog of thiols, you can imagine that they would be a little bit more acidic than thiols. That's down the periodic table. Across the periodic table, as you move across the periodic table, you also get stronger acids. And we saw this trend. Just move across the first row. The trends are pretty big. With alkanes, I'll write them as RH, like methane. I said you have a pK of about 50. R is a standard designation that organic chemists use for an alkyl group, like a methyl group, CH3, or an ethyl group, CH3, CH2. Amines, the pKa, we said about 38. Alcohols, about 17. And if you continue, you have only hydrofluoric acid, which we said is about 3.2. So in this trend, you can think about stabilizing the negative charge. All of the anions are about the same size, little differences in size, but you get a greater and greater nuclear charge as you move across the periodic table. So in this case, when you're dealing with the same row of the periodic table, you really are following electronegativity trends, and you can think of it just fluorine has more charge in the nucleus, so you're better stabilizing the negative charge. Some of these explanations I'm giving you are a little bit simplistic, and you can find research studies that will debate various explanations. The next one I'll give you is definitely one where I'm giving you the simple answer, and you can see lots of alternative explanations. As in so many cases in science, there are multiple models that can explain the same thing. We saw this, for example, in looking at Lewis structure approaches to valence, to understanding structure and bonding versus molecular orbital approaches to understanding structure and bonding. So, resonance stabilization of the conjugate base also leads to a stronger acid. If we compare an alcohol, ROH, to a carboxylic acid, RCOOH, and I'll write out the carboxylic acid structure. In both cases, you have a hydrogen and an oxygen, but the pK of an alcohol is about 17, whereas the pK of a carboxylic acid is typically about 4 to 5. So the carboxylic acid is the stronger acid than the alcohol. And the way I always like to think about this is just, in the case of the alcohol, when you deprotonate, you generate an alkoxide anion. That negative charge is localized on one oxygen. But when you deprotonate a carboxylic acid, you generate a structure where the negative charge is spread out over both oxygens by resonance. That better stabilizes the negative charge. And so that's a model that I like for understanding the greater stability of carboxylic acids. Alkanes, methane, pKa of CH4, methane, alkanes is about 50. So this is specifically sp3 hybridized. You know, once you've worked with the trends for a while, you're going to be in pretty good shape. For now, I'd say the numbers that we had today are worth having in your head. This is what I call core knowledge. The ones that are about to follow are going to show you some very specific trends. Forget about the details. But those very first ones, that's what I call core knowledge. You're going to be pulling up on those again and again in thinking about acid-base equilibria. There isn't that much that I would call really core knowledge, a few facts to have at your fingertips. But acidity is one. That's probably the one that you look and say, oh yeah, this is actually knowing some facts. All right, let's just take a look at some trends where I wouldn't expect you to know the details of the numbers, but just the principles. Inductive stabilization of the conjugate base leads to a stronger acid. Take as an example 4 compounds. Acetic acid, CH3COOH is 4.76 for its pKa. If we now start to replace these hydrogens with fluorines, the acid gets stronger and stronger. Fluoroacetic acid, CHF-COOH, has a pKa of 2.66. We call it fluoroacetic acid because one of the hydrogens has been replaced by fluorine. Difluoroacetic acid has a pKa of 1.24. CHF2COOH. And trifluoroacetic acid, CF3COOH, has a pKa of 0.23. And if we think about this, that makes a lot of sense. Here's our conjugate base of all of the carboxylic acids, but as we add fluorines, those dipoles from the carbon-fluorine bond, a polar covalent bond that's polarized toward the fluorine, those dipoles help pull the negative charge away from the carboxyl group and help stabilize the negative charge. You will, by the way, see me write structures RCOOH, RCO2H, and the full structure that I've written out for carboxylic acid almost interchangeably. And this is pretty typical in organic chemistry. All right. Last trend I want to talk about. More S character leads to stronger acid. As we compare CH bonds that have hybridization of sp3, sp2, or sp, we see big differences in the acidity. We saw that acetylene was relatively strong among the very weak acids with a pKa of about 25. Remember, the CH is sp hybridized. It was a much stronger, very weak acid than ethylene and alkenes, the sp2 hybridization. Remember, alkenes have a pKa of about 44. Pardon? Oh! Thank you. And alkenes are a little bit stronger acid than alkanes, like methane, with a pKa of about 50 and an sp3 hybridization. And what's going on here, it really is the same principle that we talked about before. When you pull off a proton, you leave behind a pair of electrons. You leave behind an anion. Those electrons, if they're in an sp orbital, have more S character. Sp is 50% S character. sp2 is 33% S character. sp3 is 25% S character. The more S character, remember the S orbitals are lower in energy than the P orbitals. The more S character, the closer those electrons are to the nucleus, the more they get stabilized. And so again, this principle of stabilization of the negative charge becomes a very good guideline for thinking about acid strength. Earlier, when I talked about positions of acid-base equilibria, I said equilibria lay very far to the right, very far to the left, etc. And then I started tossing out some numbers, 10 to the 13th difference in equilibrium constant. We're not really doing a calculation so much as an intuition. I mean, it's a calculation that can be done by an elementary school student. The principle is very simple for equilibria and position of acid-base equilibria. Let's say acid-base equilibrium. Principle is very simple. It's our equilibrium constant, KEQ, constant relating the concentration of products over the concentration of reactants, is equal to 10 to the delta pKa. As soon as I show you an example, you'll see exactly what I mean. Let's take our equilibrium between acetylene and an amide anion to give, and we already decided this equilibrium lies to the right, to give acetylide anion plus ammonia. We already looked at this and identified acetylene was our acid on the left in this acid-base equilibrium. Ammonia was our acid on the right. Acetylene has a pKa of 25. Ammonia has a pKa of 38. Our equilibrium constant, KEQ, is then equal to 10 to the difference in pKa. The number on the right minus the number on the left. 38 minus 25 equals 10 to the 13th. And that's why I was able to say with such fluidity that equilibrium lies way to the right. And then if you wanted to do a G-Chem type calculation of mixing a mole of sodium acetylide or a mole of sodium anide with a mole of acetylene and a liter of solvent like tetrahydrofuran, you could calculate the vanishingly small concentration of acetylide, just as you had done in freshman chemistry. But to a first-order approximation with an equilibrium constant of 10 to the 13, if I mix a mole of acetylene and a mole of sodium amide in a liter of solvent like tetrahydrofuran, the concentration of acetylide anion is pretty darn close to 0. And conversely, if I mixed a mole of ammonia and a mole of acetylide, what was I going to say on this? If I mixed a mole of ammonia and a mole of sodium acetylide, the concentration of acetylene would be pretty darn close to 0 as well. The last point I want to make, and this is an important one because this is where students often get confused, is don't be confused by amphoteric compounds. It's easy to get confused with molecules that can act either as an acid or as a base. So it's worth taking a moment to actually think about how a compound is acting. Let's take a specific example. Ammonia and hydroxide anion can be in equilibrium with amide anion and water. And it's very easy to get yourself confused and start to think, oh wait, water, hydronium ion, ammonia, ammonium ion. Take a moment and actually look at an equation like this and first say, all right, who's the acid, who's the base? In this equation, ammonia is giving up a proton to hydroxide. That means ammonia is acting as an acid. We're not accepting a proton to form ammonium ion. We're releasing a proton to form amide anion. Hydroxide is acting as a base. The conjugate base of ammonia is amide anion. The conjugate acid of hydroxide anion is water. We need to think about the pKa of ammonia to give up a proton. Its pKa is about 38. It's the weaker acid. pK of water is 15.7. It's the stronger acid. This equilibrium lies way to the left because we always go from the stronger acid to the weaker acid. So let me write that out just so I can codify my thought processes here. What I'm saying is NH3, we're talking a pKa of about 38, not ammonium. Which has a pKa of 9.26. And water has a pKa of 15.7, not hydronium that has a pKa of negative 1.7. And after a while, you really aren't looking at numbers. You're saying, oh yeah, I don't remember if it was negative 1.7 or negative 2. I remember hydronium was a strong acid. And I know hydroxide, I know water is somewhere about the same as an alcohol. And if you don't remember, it's 15.7. You say, well, water is somewhere around 17. And that's when you get it. All right, next time we will talk about Lewis acids and Lewis bases and lead the way to thinking about nucleophiles